basically what happens is that we first of all try to look at this and we say SO reads the A. So we can say A, B, and C. Reads the A, stays on SO. Reads the B, stays on SO. Reads the C, goes on SO. Reads the A, goes on S1. So then an S1 reads the A, does nothing. Reads the B, goes on S1. Reads the C, goes to S2. On S2, which is our accepting state, reads the A, stays on S2. Reads the B, stays on S2. Reads the C, stays on S2. Now, the important thing to convert to a DFA is that we write the first blank as it is. So we say SO, SO, S1, SO, and SO. Then we slowly try to expand it. We expand SO, S1, and we look at SO, S1 both at the same time. On A, SO, S1 goes on SO, S1. On B, it goes SO, S1. And on C, it goes SO, S2. Let's try to convert this. We have SO, S1. We have SO. We have S1 and we have S2. SO, S1 reads the A, goes on its own. Reads a B, goes on SO. On C, goes on SO. Oh, sorry. SO reads a A, goes here. Reads a B, goes on its own. Reads a C, goes on its own. Then on SO, S1, reads a A, goes on its own. Reads a B, goes on its own. But when it reads a C, it goes on SO, S2. Oh, this we have not opened. SO, S2. We need to make another one. S1, S2, SO, S2. So SO, S2 reads A, SO, and S2. Now we look. SO, S1, S2. Now we got something new. SO, S1, S2. We need to open this too. Reads a B, SO, S2. Reads a C, SO, S2. So this one reads A, goes on this new state that's called S1, SO, S1, S2. Then after reading A, it goes here. Now what we see is that SO, S2 reads the A, goes to the state that we talked about. So basically now we see the states. Now we see SO, S2 reads the A, goes to this one. Reads a B, stays on its own. Reads a C, stays on its own. Then the next state we can see the same, all three at the same time. Now look at all three at the same time. SO, S1, S2 at A, SO, S1, S2. On B, SO S1 S2. Yes, SO S1 S2. SO S1 S2. On C, SO S2. SO S2. So this state basically on A and B goes on its own, but on C it goes on SO S2. And basically these were our states. And we had S1 and S2. S1 basically goes reading a B on its own. Yeah, we forgot one arrow that it reads a C when it goes there to SO S2. Here we see it reads a C, goes to SOS2. And because there is no configuration for anything else, everything else looks perfect. Now we can see our machine looks something like this. It looks like SO S1 SO SO S2 SO S1 S2, where this goes to itself reading AB, and it goes to SOS2 reading a C. It goes reading on its own B comma C. It goes SOS2. How about when it reads A, SOS2, SO S1 S2, S1 S2, yeah, it reads A, then it goes here. And now we have SO BC and reads A, B comma C reads A, goes here, and SOS1 AB and C, C going to SOS2. It's a little complicated diagram, but this is how it is. A comma B. Yeah. So you can do A, B, and when you do C, you go there. Now what it told us was that specify that describes the language recognized by the above automation. I think a more cleaner version will be something like this. It's the same exact diagram that we have, but here he made it more clean because he made SO, SOS1, SOS2, and then like this. This is how we get the final automation. And a regular expression looks something like this, where A, B, C are a choice. You can do B, C, or A. Write as many A, B, C's as you like. So B, C, B, C, B, C, B, C, and A. Then you must do a. This is the must do A phase. Then as many combinations A has to be written to reach the next state. Then B are infinite. Write as many B's as you like. And C needs to be a condition that is must. And then we have a choice between, again, A, B, C, as many times B's, A's, and C's as you want, because you can do A, B, C, and A, B, C as many times as you want. So expression should look something like this, that A, comma, B, comma, C as many times as you want. And A, because is a must to move forward, just like we have it here. You can see this A. Then we have a B that is as many times as you want. You can repeat B. And you have a C. you can see ABC was a choice. See this one we look. It's easier to make a from the actual. For example, what was the actual question? Look at this. It's so easy. You just look at the NFA. You don't look at the DFA to make the regular expression. It's so easy to look at this and make, for example, the first one was A, comma B, comma C. Of course, this is what it looks like. As many times as you want. You can repeat because it's a loop. Then you must take a A to move forward. Then B is a loop. Then must take a C to move forward. Then A, comma B, comma C. It makes a lot of sense, right? That is the regular expression for this one. And then we know the method to convert it into a DFA. Then we can do the same method apply that we learned on this one. And then the DFA for this one should be, regular should be A, comma B, comma C. As many times as you want. Then we can do A. Then we can do C. Then we can do A, comma B, comma C as many times as we want. And to be, but actually you can do C or B. Also, you were never asked to make a regular for this one regular expression, so forget about it. You just need to make a DFA for it, and you need to make a complement. So make the accepting, non-accepting, that's the complement, and accepting the non-accepting and accepting, just reverse the states of accepting and non-accepting, then you have a complement of it. And then the next question would be this one, which would want you to be divisible. The zeros is even, 0, 0 is even, and then the same thing that we had. And the word does not contain 3 consecutive zeros. So 0, 0, 0 is not possible. So we make these accepting, and then the final 0 we make non-accepting, and that we allow 0, 1. This is easily convertible to grammar rules, and regular expression for this is also pretty much easy. Because then you can say 1 can be looped as many times as you want, or write as many ones as you like. 0 must be there as many ones as you want. 0 must be there as many ones as you want. Only write twice zeros at once, either 2 consecutive zeros or a 1 in between. So 2 consecutive zeros or 1 in between. Write as many ones as you want. So this is for this one, even number of zeros. And the concatenation just connects the final state for one automation within the start state of the other final state of second automation become final states of combined. So we can see this. And this pretty much is concatenation here. Then we have for selection, or just create a new start state and connect it to all previous states via the epsilon transition. So you make the even one and that does not contain 1, and you make epsilon and you translate with a union. With intersection, it's an and. You have to construct the product automation, and we have learned how to do that. And that was it. That was everything. Looking at this regular expression for even number of zeros, I think there is a better solution which enforces us that 1 is outside because 1 doesn't matter. You can say even number of zeros. I think this should also work. Sorry. Something like this. This should also work, where you can decide as many ones as you want, but then when you take no, if you just take this and do nothing, you can do that. But if you take this bracket, then 0 comes as even numbers.